In this lesson, we are going to talk about the derivative of exponential functions and the derivative of log functions. And then when we talk about the function e to the x, that's definitely an exponential function with the base e. And when we take the derivative of e to the x, we actually get e to the x. Now, if we had some other function in the exponent other than x, we would have to use the chain rule. So that's why in general we state down here, if you take the derivative of e to some power, just some other function g of x, you have to write e to that power and then multiply it by the derivative of that exponent. So whatever that g of x is, you're going to multiply by the derivative of g of x. So if you think of tangent to x as the g of x in that theorem, when I take the derivative of g of x, I'm going to get secant squared 2x, and then I have to multiply that by the derivative of the inside function, which is 2. So I get 2 secant squared 2x. So that's the derivative of the function g of x, which is the exponent. So now when we take the derivative of f of x, we're going to write e to the tangent 2x, and then we're going to multiply it by the derivative of g of x, which is the 2 secant squared 2x. So now in the next example, we're going to use the quotient rule with the derivative of the natural exponential function, what we just learned. So think of this is f and this is g. So the top function is f, the bottom function is g. So f of x is equal to e to the x squared. If I take the derivative of f, that's going to be e to the x squared times the derivative of x squared, which is 2x. G of x is x, so g prime of x is just 1. So now when we use the quotient rule, we're going to have the derivative of f times g minus the derivative of g times f all over g squared. So I'm going to have, when I do my substitutions, I'm going to have e to the x squared times 2x, that's my f prime, times my g, which is times x again, minus the derivative of g, which is 1, times f, which is e to the x squared, and then all over g squared, which would be x squared. Now the only thing we can really do to clean this up is we can factor out an e to the x squared from both terms in the numerator, and I would have 2x squared left, and then a minus 1, and that's all over x squared. So here's the derivative of e to the x squared all divided by x using the quotient rule and our new rule which deals with derivatives of the natural exponential function. The next example is using our new rule of the derivative of the natural exponential function with the product rule. So let this be my f, this be my g. So f is going to be x, and g is going to be e to the 2x. So when I take the derivative of f, I get 1. And when I take the derivative of g, that's going to be e to the 2x times the derivative of 2x, which is 2. Now I'm going to use my product rule, the derivative of f times g plus the derivative of g times f. So f prime is 1, g is e to the 2x, plus g prime is e to the 2x times 2, and f is x. So that gives me e to the 2x plus, and then I have 2x times e to the 2x. If I want, I can factor out the e to the 2x again, and I can rewrite it as 1 plus 2x. In the next example, it says applying the natural exponential function, and it says a colony of mosquitoes has an initial population of 1,000, and after t days, the population is given by the function a, which is equal to 1,000 e to the 0.3t. And we're going to show that the ratio of the rate of change of the population to the population is constant. So what we want to show is if I take the derivative, which is the rate of change of the population, and I divide that by the population, which is our function that's given a of t, that's just going to be some constant. And that's what they mean by showing the ratio of the rate of change to the population. The ratio means you're going to take the rate of change on top and divide it by the a of t in the denominator. So when we take and we find the derivative of a of t, we rewrite the function, so we have 1,000 e to the 0.3t, but then we multiply by the derivative of the exponent, which would be 0.3. And so when we take 1,000 times 0.3, that's going to give us 300 e to the 0.3t. So that's our derivative. Now when I take the derivative, which is this, and I divide it by a of t, which is the 1,000 e to the 0.3t, we're going to show that it's equal to some constant number. So I have 300 e to the 0.3t all over 1,000 e to the 0.3t. Now I can simplify this because on the top and the bottom they both have e to the 0.3t, so I can get rid of that. And now I have 300 over 1,000, which is equal to 0.3. So there is our constant, 0.3. Okay, now we're going to talk about the derivative of the natural logarithm. So that's your ln x. When you take the derivative of the natural logarithm, if your ln has some other function inside here other than x, your derivative is going to be 1 over that function, and then you multiply it by the derivative of that inner function. Now, when you're doing that with just the natural log of x, you would have 1 over x times the derivative of x, which is 1. So if it's just ln x, then you end up with the derivative 1 over x. But if you have some other function in there other than x, and you have to multiply it by the derivative of that inner function. So this example says find the derivative of f of x of the natural log of x to the third plus 3x minus 4. So if I take the derivative of f using that rule we just learned, g of x is going to be that inner function x to the third plus 3x minus 4. So I'm going to find 1 over g of x, which is x to the third plus 3x minus 4, and then I'm going to multiply it by the derivative of g of x, and the derivative of g of x is 3x squared plus 3. So this gets multiplied by 3x squared plus 3. Now when I multiply that out and I go across the tops, I'm going to write a 1 under here so things line up. When I go across the top, I have 1 times 3x squared plus 3, so I get 3x squared plus 3 in the numerator, and that's all over x to the third plus 3x minus 4. In this example, we're going to find the derivative of f of x, which is the natural log of x squared times sine x, all divided by 2x plus 1. Now, there are two ways that we can do this. We can let the inner function of g of x be x squared times sine x all over 2x plus 1, and then use the product rule and the quotient rule to find the derivative of g. Or, before you even take the derivative, use your natural logarithm properties to break this up into smaller pieces. So if you recall, using the properties of logarithms, if you have a log of some kind of quotient, you can take the natural log of the top minus the natural log of whatever's on the bottom. And then when you have a product, like x squared times sine, you can split that up into the natural log of x squared plus the natural log of sine x. So at this point, I didn't take the derivative yet. I'm just rewriting this in a way that makes it a little bit easier to find the derivative. So now if I take the derivative of each term, it's a little bit easier rather than trying to find, which you can do, but it's a little bit harder and takes a little bit more time to use the product rule and the quotient rule on that inner function g of x. So from here, when I go to take the derivative, so I'm going to write d dx, I'm going to take the derivative of this. I'm going to take the derivative of each term separately using our natural logarithm rule. So natural log of x squared is 1 over x squared times the derivative of x squared, which is 2x, plus 1 over sine x times the derivative of sine x, which is cosine x, then minus 1 over 2x plus 1 times the derivative of 2x plus 1, which is 2. Now when I simplify this, I'm going to have 2x over x squared for this first term. And when I simplify it, I get 2 over x. When I simplify that 1 over sine x times cosine x, that gives me cosine x over sine x, which is cotangent x. And when I take 2 times 1 over 2x plus 1, that just simply gives me 2 over 2x plus 1. So here's our derivative of the natural log of x squared times sine x all over 2x plus 1. Now, if you wanted to use the method where you take, to find the derivative, you take 1 over whatever's inside the parentheses, so that would be x squared times sine x all over 2x plus 1, and then multiply it by the derivative of that inner function. You can totally do that, but you should still get the same thing. It might be a little bit lengthier, but you should still get the same thing. And that would be a really good exercise for you to try for practice. Now, in general, we have rules for exponential and log functions when we take the derivative. The natural exponential function and the natural log function are special cases of this, but it still falls under this umbrella, and I'll show you here in just a second. The general rule for logs, if you have a log of base b, x, then what you're going to do is you're going to take 1 over whatever that inner function is, so whatever this inner function is here, times the natural log of your base b. So see, this is base b, so when you take the derivative, it's 1 over whatever that inner function is times the base b, or times the natural log of base b. Now the reason why the natural log of x is just 1 over x when I take the derivative, by following this rule, I would take the 1 over x, that's my inner function, and then I would multiply in the denominator times the natural log of the base of the natural log, which is e. And the natural log of e is just 1, and then when you have 1 over x times 1, you just get 1 over x. So this is still following this rule, it's just a special case. Now, here it is down here written with a different value other than x. You take whatever that inner function is, that goes in the denominator with the natural log of the base, and then you multiply it by the derivative of that inner function. Now, if you're talking about the general form of an exponential function, if you have b to some exponent, like a base, like say 5 to the 3x. So your base is b, and your g of x, your exponent, is 3x. So you would write that exponential function again, and then you multiply it by the derivative of your exponent, and then times the natural log of whatever your base is. So the reason why e to the x, when you take the derivative, is e to the x, it still falls under this umbrella. My base is e, so if I follow this rule, I would write e to the x times the derivative of x, which is 1, times the natural log of my base, which is e. And the natural log of e is 1. So I would still get e to the x. In this next example, we're going to use the quotient rule along with the new rule that we just learned for the derivative of an exponential function to find the derivative of this function h of x. So we have the top function, we'll call that f, and then we have the bottom function, we'll call that g. So f of x is going to be 3 to the x, and so when I take the derivative of f of x, I'm going to rewrite it, so 3 to the x times the derivative of the exponent, so the derivative of x is just 1, and then times the natural log of the base, which is 3. I'm going to multiply it by the natural log of 3. So this is 3 to the x times the natural log of 3. For the function g of x, we have 3 to the x plus 2. When I take the derivative of g of x, I'm actually going to get the same derivative of f of x because I just have a plus 2 on the end. And when I take the derivative of plus 2, that's just 0 because I'm taking the derivative of a constant. So my derivative for g of x is going to be 3 to the x natural log of 3 as well. So now when I apply the quotient rule, I have the derivative of f times g minus the derivative of g times f all over g squared. So f prime is 3 to the x natural log of 3. And then when I multiply by g, I get 3 to the x plus 2. And then I subtract g prime, which is 3 to the x natural log 3, times f, which is 3 to the x. And then this is all going to be over g squared. So that's 3 to the x plus 2 squared. So now, really the only thing I can do to simplify this is in the top, I can pull out a 3 to the x natural log 3. And what's left over, whoops, I'm not giving myself enough space here. 3 to the x natural log 3. And what's left over is 3 to the x plus 2 minus 3 to the x all over 3 to the x plus 2 squared. Now, this 3 to the x minus the 3 to the x disappear. So, I can clean that up a little bit and write 2 times 3 to the x natural log of 3 all over 3 to the x plus 2 squared. The next example, we are going to find the slope of the line tangent to the graph of y equals log base 2, 3x plus 1 at x equals 1. So in this question, it doesn't ask for the actual equation of the tangent line. It's just asking for the slope. So really all we have to do is find the derivative and then evaluate it at x equals 1. So when I take the derivative of y, I'm going to have y prime. Now the derivative of any log function was 1 over whatever that inner function is. So that's 3x plus 1. In this next example, we're going to find the slope of a tangent line. So we don't actually have to find the entire equation, just the slope. And so all we really have to do is find the derivative of y and then evaluate it at x equals 1. So to find the derivative of y, we write 1 over whatever that inner function is, so 3x plus 1, and that's going to be times the natural log of whatever the base is, and the base is 2, so it's going to be the natural log of 2. So we have 1 over 3x plus 1 natural log of 2. So keep in mind that that natural log of 2 is in the denominator. And then I have to multiply it by the derivative of that inner function. So I'm going to take the derivative of 3x plus 1, which is 3. So I'm going to get 3 over 3x plus 1 times the natural log of 2. And I'm going to evaluate that at x equals 1. So I'm going to plug in 1, and that's going to give me 3 over 4 times the natural log of 2. And there really isn't anything else you can do to simplify that, so we're done here. The last topic that we're going to go over in this section is called logarithmic differentiation. And so sometimes it's really hard to take the derivative of a function in the form of g of x raised to some power if it's kind of an awkward function. So there are times where it's easier to use this logarithmic differentiation. All it does is it uses the properties of logarithms to pull that exponent down in front and then use our regular differentiation rules. So the first thing you want to do when you use this problem-solving strategy is, for step 1, you are going to take the natural logarithm of both sides. So it has to be the ln. So you're going to do ln of both sides of the equation. And then you're going to use the properties of logarithms to expand your expression as much as possible. That's step 2. Then step 3 is you're going to take the derivative of both sides. Then you can solve for dy dx and then resubstitute your h of x. In this example here, we have kind of an odd function where we have 2x to the 4th plus 1 all raised to the tangent x. Let's try using the logarithmic differentiation. So we're going to take the natural log of both sides. And then we're going to use logarithmic properties to expand this and simplify it as much as possible. So I have natural log of y is equal to, now I can bring that tan x down in front. So I have tan x times the natural log of 2x to the 4th plus 1. Now when I take the derivative of both sides, I'm going to have the derivative of the natural log of y is 1 over y times the derivative of y, using the chain rule, dy dx, is equal to, now on this side, we have to use the product rule. So we're going to let this be f, and we'll let this be g. So if f is tangent x, then f prime is going to be secant squared x. And if g is the natural log of 2x to the fourth plus 1, then g prime is going to be 1 over 2x to the fourth plus 1 times the derivative of 2x to the fourth plus 1, which is 8x to the third. So when I simplify this, I get 8x to the third all over 2x to the fourth plus 1. So now when I fill this in and I take the derivative using the product rule, I'm going to take the derivative of f, which is secant squared x, times g, which is the natural log of 2x to the fourth plus 1, plus the derivative of g, which is 8x to the third over 2x to the fourth plus 1, times f, which is tangent x. Now, when I multiply both sides of the equation by y to clear this 1 over y, I get dy dx is equal to y times secant squared x times natural log of 2x to the fourth plus 1 plus 8x to the third over 2x to the fourth plus 1 times tangent x. So all of this is being multiplied by y. And now what we're going to do is to finally finish this, I'm going to resubstitute what y is equal to in for here. So we have everything in terms of x. So I'm just going to put in here 2x to the fourth plus 1 raised to the tangent x. And then everything in the bracket stays the same. I'm just going to carry it down. Secant squared x times the natural log of 2x to the fourth plus 1 plus 8x to the third over 2x to the fourth plus 1 times tangent x, all in brackets. You take the log of both sides, you use the properties of the logarithms to bring that exponent down in front, and then you use any of our differentiation rules, including implicit differentiation, to take the derivative of both sides, and then you have to resubstitute in your original function. Okay, let's try one more example with that. So for this one, we're going to do the same thing. We're going to use the logarithmic differentiation. I'm going to take the log of both sides, natural log specifically, and now I'm going to use the rules of logarithms to expand this. So the natural log of x times the square root of 2x plus 1 all over e to the x times sine cubed x. When I expand that, I'm going to get the natural log of x plus 1/2 natural log of 2x plus 1 minus x natural log of e, which we can change this into a 1, minus 3 natural log of sine x. So now when I take the derivative of both sides, I'm going to get 1 over y times dy dx, and that's going to be equal to the derivative of log x, which is 1 over x, plus the derivative of 1/2 log, natural log of 2x plus 1, which is 1/2 times 1 over 2x plus 1 times the derivative of 2x plus 1, which is 2, minus the derivative of just x, because this crossed off and gave us a 1, so that's minus 1, and then minus 3 of 1 over sine x times the derivative of sine x, which is cosine x. So that's going to give me 1 over x plus this 2 and this 2 cross off, so I'm left with 1 over 2x plus 1. And then I have a minus 1 and a minus 3. And when I multiply these together, cosine x over sine x, that's going to give me cotangent x. Oh, I forgot my 1 over y here. So now I have to multiply both sides by y and then resubstitute that y back in. So when I multiply both sides by y, I get y times all of that, and then these y's cross off. And so I'm going to get dy dx is equal to, I substitute that y back in, so I have x times the square root of 2x plus 1 all over e to the x times sine cubed x, and then all times 1 over x plus 1 over 2x plus 1 minus 1 minus 3 cotangent x.